Good morning everyone and welcome to my YouTube channel. So as for today, we are just going to be looking at dimensional analysis practice problems. So we are going to do a lot of questions. So if you are new to this YouTube channel, kindly like, subscribe and share for more. If this is your first video, kindly just watch the introduction to dimensional analysis so that it's much easier to follow. So firstly, we are going to be looking at questions that deal with dimensional analysis. Now, we cannot necessarily do this direct without looking at the principle of homogeneity. So what does this principle talk about? So it simply says that only like terms can be added, subtracted, or equated. This is very important as we answer questions. So what does this tell you? Let's say, for example, if we have our A should be equal to B plus C. So this means that if you are just able to add B plus C, it means to say whatever dimensions are on B are the same as the dimensions that are on C. So these are more like the same. That also means to say the dimensions for A can also be equal to B, as well as the dimensions for A can also be equal to C. That is what we mean by only alike dimensions can be added, subtracted, or equated. If you see this means to say the A dimensions are here. At the same time, the A dimensions can also be at C. That means also that our dimensions that are at B are the same as the dimensions that are at C. That means that B can also be equal to C in terms of dimensions. That's the only reason why you are able to add them. So now, with that said, let us be able to answer questions. So let's say we have shown that the equation is dimensionally correct. So how do we do this? Let's begin with a simple one. Let's say the equation was originally V should be equal to U plus AT. So how you find whether or not this equation is dimensionally correct is that you should have the same units. So like for example, your velocity, we know that our velocity is equal to L t raised to the power negative 1, like that. So this is our dimensions for velocity. Just in case you are watching this video, just watch the introduction, how we introduce this. So we are going to have our L t raised to the power negative 1, where there is V. Now U is also the velocity, meaning to say it will still have the same dimensions. So L t raised to the power negative 1. So we are going to put L t raised to the power negative 1. Then we have plus, what is our A value? So to find our A value, we know that our acceleration according to the dimensions should be equal to, we have our L t raised to the power negative 2. So we can put it here, our L t raised to the power negative 2, like that. Then we have our times, our time, which is equal to just a t to the power 1. This is U plus AT. So if we have this equation, this is how we deal with it. So we are going to have our L t raised to the power negative 1 should be equal to, we have our L t raised to the power negative 1, like that. Then we have plus. Now here, we know that if we are multiplying our LT, we can have L t raised to the power negative 1. If we multiply t times t, that it means to say we add the powers according to the rules of indices. So here we are going to have our L t raised to the power negative 1 should be equal to L t raised to the power negative 1, like that. Then we have plus, we have our L t raised to the power negative 1 plus 1, negative 2 plus 1 gives you negative 1, like that. So that means to say, as you can see, since these are the same, and the coefficient here in front we have 1 and we have a 1, like that. So we can just add them normally by saying what is 1 plus 1, which is our 2. So we have our L t raised to the power negative 1 should be 1 plus 1 is 2. Then we have our L t raised to the power negative 1, like that. So already, if the dimensions that are this side are the same as the dimensions that are this side, then your equation is said to be dimensionally correct. Now, you don't worry about these two. A pure number, is dimensionless. So I have already introduced all these things So if you are watching this video for the first time, kindly go back to the first one, which is our introduction to dimensional analysis. So a 2 is dimensionless. The only dimensions we have are LT raised to the power -1. Now, if according to this, the principle of homogeneity matches up in the sense that the dimensions that are on the other side of the equal sign are the same. So let us also be able to now solve the other question. So for this problem, we say that v squared is equal to u squared plus our 2as. So we know that our v is equal to lt raised to the power -1, like that. Then we also know that our u should be equal to our velocity, which is our lt raised to the power -1. Then we also have our acceleration to be lt raised to the power -2. Then s is the distance, meaning to say s will just take l. So we can replace this by saying our final velocity is lt raised to the power -1, but it is squared, so we put the square like that. Also, our initial velocity, which will also be equal to lt raised to the power -1, then we have to the power 2, then we have plus, then you are going to add plus. We have our acceleration is lt raised to the power -2, so we are going to put our lt raised to the power -2 like that. Yeah, then we have our s. Let's just delete the velocity. So then our s shall be assigned the unique letter l, which means the length, like that. So we are going to have so this squared, these two can be distributed. We are going to have l to the power 2, t to the power -2 should be equal to, we have even these two distributes, we have l to the power 2 and we have t to the power -2, like that. So that's the way it works. So this 2 times -1, that's 2. This 2 comes here. Then we have plus. Now what we are going to have is, we have our l, it is to the power 1, even this l is to the power 1. So we are going to have our l to the power 1 times l to the power 1, it will be, so we have a 2 in front. So we have a 2 in front, we have say plus 2, then we are going to have our l to the power, so we have 1 plus 1, l to the power 1 times l to the power 1 is 1 plus 1, then we have our t raised to the power -2, like that. Then what we are going to have is we have our lt raised to the power -2 should be equal to, we have our l to the power 2 t raised to the power -2, then we have plus our 2, l to the power 1 plus 1 is l to the power 2, then we have t to the power -2, like that. So now already this and this are the same, so we can just add them. So we have our l t raised to the power -2, like that, should be equal to, when we add 1 plus 2 will give you, so we have the dimensions in these brackets. So we are going to have our 1 plus 2. Since these are the same, we can just add them normally. 1 plus 2 gives us 3, l to the power 2, t to the power -2, like that. So same approach. Since the dimensions are the same, we can even conclude that since the dimensions, I'll just use this, the dimensions on the left hand side, you can just write it in full. Left hand side are the same as the dimensions on the right hand side, then it is dimensionally correct. Remember, the 3 is dimensionless, it doesn't have any dimensions. Let's look at our question 4. We have our example 4. The distance x in meters, the time t in seconds, and the velocity v in meters per second. What are the dimensions and SI units of A, B, C, D, and E? So now we know that we have our x should be equal to A VT, then we have plus B sine of our CT, then we have our D, we have plus our D t to the power 1 over 2, then we have our 3 to the power x over e, like that. So how do we find the values of these? So firstly, here what we are going to do is we are just going to answer not like in any particular order. Whatever is easy to find, we are going to find. So now, using the principle of homogeneity, where the units that are on your left are the same as the units that are there. As long as you're adding these, that means to say the dimensions that are here are the same as the dimensions that are here are the same as the dimensions that are here. So all these dimensions, when you look at this, they should give you x. That's how come when we were finding our LT raised to the power negative 1, which was equal to the initial, it was LT raised to the power negative 1. Even the units that were there, it was still LT raised to the power negative 1. So this means that is, by the way, v should be equal to u plus at. When we found this, we were reaching this conclusion. So whatever units are here are the same as what are here, are the same as those that are here. So now, with that said, what we are going to do is this. We are just going to sometimes be equating and sometimes using the rules. Firstly, let's go with some things that we can easily find in no particular order. For example, we have the b sine of a ct like that. So now, just getting the sine of our ct, we are going to say, according to dimensional analysis, the trigonometric exponentials and logarithms are considered to be dimensionless. So if you see your ct, if t is the time, that means to say c must be the reciprocal of your time t. So already, just by looking at this, it means to say your c is equal to 1 over the time. So that when you put your c there, it can be able to cancel with this time. So now let me make you an easy way to remember, to know how to find the values. So according to dimensional analysis, trigonometric ratios are considered to be dimensionless. So we can say that we will just get what is in the brackets. You have your ct, just equate it to positive 1, so that you show that it should give me a pure number. So you can just divide over the time like that. So the dimensions of c are that time we will use a capital letter, so it will be 1 over your time like that. So these are the dimensions of c, which can also be written as our t raised to the power negative 1 like that. So this is how we do that one. The SI units we are going to be having, according to this, we are going to have our second to the power negative 1, because time will assume the second. That's the SI unit for time. Now it is raised to the power negative 1 like that. So after doing that, we can now find our b. So according to this, I have told you to say, according to the principle of homogeneity, if here it is x, here we should have x, here we should have x, and here we should also have x like that. So if that's the case, we can also be able to say already your x should be equal to, we can say, our b sine of our c t like that. Now already you know that this is dimensionless, because the sign of the trigonometric ratios are considered to be dimensionless. So that means to say what you remain with is your x should be equal to your b. Where there is sign, you can just put a pure number, so that you show that the sign is dimensionless. So this means that x is equal to b, and b, according to this, we are provided that our x is in meters, meaning to say distance is in meters. The dimensions for distance will assume the letter length for L. So distance is just length, so we can say that this is our dimension for length like that. So if that's the case, then the SI units for our b SI units for our B, we can say that it should be equal to the meter, like that. So this is our SI units. So we have found our value of our B and C. So let's also find our E. So according to E, we have been told that where E is connected to, we have our D, t raised to the power half, then we have 3x to the power like this. Now, according to dimensional analysis, we have been told that the exponentials are considered to be dimensionless, like this one. Exponentials of numbers are considered to be dimensionless. So we are going to have already, we have our 3. Let's just isolate our 3x over E. That's the meaning of our over E there. So we are going to use the same approach. So it means that our x over our E should be equal to 1. So you can just attach a reasoning to say, if you want, you can just go direct to say, for us to have a pure number, the dimensions of x must be the same as the dimensions of E, since these are dividing. But using this helps you. So you are going to just cross multiply to find you have your x should be equal to just E. So equating to the unique number 1 helps you know the dimensions of the other variable. So we have our x should be equal to E. Now we know that our dimensions of x is the distance, meaning to say it's L. So L is equal to E, like that. Then the SI units for E, it will be equal to the meter, like that. Now getting our dt to the power half, so we are going to have our dt to the power half. So just as we have discussed, the dimensions that are here are the same as the dimensions that are here. So extracting our dt to the power half, 3 to the power x over E. So this means that we know that the pure number, the exponent of a pure number, is considered to be dimensionless. So what we are going to have is we can just equate this whole thing to be equal to x, since the dimensions that are here are x, dimensions that are here are x, dimensions that are there are x. So this means that your x is only equal to d t raised to the power half, like that. Then we have our dimensionless constant. We can just put a 1, like that. So already we can now be able to leave d alone by dividing our t half, like that, our t half, like that. Now to come up with the dimensions, this is what we are going to have. Our dimensions of our d will be equal to, we have what is our x. X is a distance, so it will be length over time t, which will be your t to the power of half, like that. So these are our dimensions of our time, like that, which can be written in the form, if you want, your L, then the t goes up, this power becomes negative, it will be t raised to the power negative half, like that. So now these are the dimensions of d. Then the SI units will be equal to, we are going to put our length is the meter, then time is the seconds, then to the power half, like that. So we have found our B, we have found our C, we have found our D, and we have found our E. So what we need to now find is just A. So still we are going to get our X should be equal to, we have our A VT, like that. So already we are going to equate them. So our A VT should be equal to X. So how do we find our X? We know that the dimensions of velocity are LT raised to the power negative 1. So where there is x first, we put L should be equal to, we have our A, like that. Then the velocity is LT raised to the power negative 1, like that. Then we have our time, which is our t, should be the capital letter T, like that. So we are going to have our L should be equal to A, then we have our LT, then negative 1. If they are multiplying, they can add up. So we are going to have plus 1, like that. So we are going to have our L should be equal to A, then we have our L, like that. Then what we are going to have is we are going to divide over our L to leave A alone, over our L like that. So when we do this, we are going to divide. Now what we are getting is A1. 1 should be equal to A. What does this tell you? It means that A is dimensionless. So A is dimensionless. So that is the way it is. So we have found our values. So we have our A is dimensionless. So those are our dimensions. So for our next question is saying that in the gas equation, this one, where P is the pressure, V is the volume, R is the universal gas constant, and T is the temperature. What are the dimensions of A and P? So firstly, we have our equation which is saying that we have a P plus A over our V squared. Then we also have our V minus B, which should be equal to RT. So now remember, as long as, according to the principle of homogeneity, as long as you are adding two quantities, whatever dimensions are at P are the same as the dimensions that are not necessarily A, but are the same dimensions as this whole thing. So what we are going to say is, already our pressure should be equal to A over V squared. So we can now be able to cross multiply, in which we are going to have P should be equal to crossing multiply P times V, it will be P V squared should be equal to our A like that. So that means that we have our pressure and our volume, but these we want to stick to our dimensions, which are our length, time, and mass if possible. So we know that the pressure is equal to force over the area, and we know that the force is a product of mass times acceleration according to Newton's second law. So we are going to have mass, which is capital delta M, then our acceleration, which should be equal to our acceleration, which is equal to our L t raised to the power negative 2. So these are dimensions for acceleration over the area. So if you look at your area is equal to length times breadth. So in other words, our length times breadth, all of them are just lengths. Others will even have length times length, which is your L squared. So you are going to say, so this is already your force, which is your MLT raised to the power that. So we are going to have our MLT raised to the power negative 2 like that. So we are going to put that our pressure should be equal to our force is MLT raised to the power negative 2 over what is our area. Our area is L squared. So we can put the L squared there. So we are going to have pressure should be equal to mass. Then we have our length. Length is raised to the power 1. So what we do is to take the L up there. We are going to say minus 2. Since L is the same, we just take one L and subtract the power. So we have T raised to the power negative 2 like that. So the pressure should be equal to, we have our M, L negative 1, T raised to the power negative 2 like that. So this is our dimensions for pressure. So already these are our dimensions for pressure. and we have our volume. Volume is length times length times length, which should be equal to L to the power 3. So the dimensions of volume are L to the power 3, like that. Now remember, what we got was our A. Our A should be equal to V PV squared. So what we are going to do is we are going to replace now. So already our pressure is this, so we can just be able to say our A should be equal to, so our pressure is our L raised to the power -1. Then we have our T raised to the power -2 times the volume is L cubed. So we can put L cubed like that, but it's power 2 to the power 2. So we are going to have should be equal to A. So we have our L to the power -1, T raised to the power -2. Then 3 times 2 will give us L to the power 6 should be equal to A, like that. So we are going to now multiply. So our M, then we have our L raised to the power -1. You take one L and add the powers if you are multiplying. So T raised to the power -2 should be equal to A. So we have our M, L raised to the power +5, like that. Then we have T raised to the power -. So this should be equal to our A, like that. So these are our dimensions. Let's look at our B. For our B, this is what we have. So now for you, we have our P plus A over V squared. Then we have our V minus B should be equal to RT. Now, according to the principle of homogeneity, only like terms can be added or subtracted. So if we have V minus B, it means to say the dimensions of V are the same as the dimensions that are there. So we have V should be equal to B without considering the sign. So we are going to say, if volume, this is our volume, we said that it is L to the power 3, which should be equal to B. So this is our dimensions of B. So dimensions of B are L to the power of 3. That means that we have answered that. We found our A to be our M, L to the power 5, T to the power -2, like that. So these are our dimensions. Looking at this, the law of radioactive decay is given by the formula. So we have our NT should be equal to NO. Then we have E to the power negative, that where N0 is the number of radioactive nuclei at T is equal to 0, NT is the number of remaining. And this is the quantity known as the decay constant. What are the dimensions of this? So now, already, you're just going to get this part that is having the exponential. So your E to the power negative lambda T. Now, by argument, we know that the trigonometric exponentials and logarithms are considered to be dimensionless. So what you can do is just say lambda T should be equal to 1. Then you're going to divide over T. Then your lambda should be equal to your 1 over your T, like that. So if that's the case, it means to say the dimensions of lambda should be equal to 1 over the T, capital letter T, since it's time. So already your dimensions can be written like this, or T raised to the power -1. So that is how we find that. So let's say we have been given if the units of length, mass, and force are chosen as fundamental units, what will be the dimensions of time in terms of the dimensions of these units? So already we have been given force, mass, and length. So now what we are going to begin to do is we are going to say our force. We need a formula that can connect our mass and length. Now indirectly, we know that the acceleration has dimensions L T raised to the power -2. So we can say that our force should be equal to, we have our mass, so we have the force, according to Newton's second law, is given as force is the product of mass times the acceleration. So we know that in terms of dimensions, this can be written as, we want the dimensions of time. So this is one of the formulas that can connect force and time. So we can say force should be equal to, we have our big letter M, then we have the acceleration is our L t raised to the power negative 2, like that. So if that's the case, all we have to do is make t the subject of the formula. So this is the same as force should be equal to M L t raised to the power negative 2, like that, which can be written as force should be equal to M L, then we have over the time to the power 2, like that. So we can be able to do this, then cross multiply. So what we are going to have is our ft, f times t squared, it will be ft squared should be equal to ml, like that. So after doing that, we are going to get over our force, like that. So this is what we have. Our time squared should be equal to, we have our ml over the force, like that. But we need to find the square root so that we eliminate this square. Then what we do on one side, we have to do it on the other side. So your t should be equal to the square root of our ml over the f. Now this can be distributed. We must leave them in terms of exponentials. So it will be ml over the force, like that. Then raise this to the power. Since the square root also means half, so we can now be able to say our t should be equal to m to the power of half. Then we have L to the power of half over our F to the power of half. Now remember, the question was saying that the length, mass, and force are taken to be dimensions. So already that means to say we don't have to go further to describe what our force, the dimensions of force is, because it is taken as a dimensional force itself. So it is going to end like this for this one. Okay, so looking at this other example, suppose we are told that the acceleration of a particle moving with uniform speed v in a circle of radius r is proportional to some power of r, say r to the power n, and some power of v, say v to the power m. Determine the value of n and m and write the simplest form of the equation for the acceleration. So we have been told that the acceleration is proportional to, so we have the acceleration is proportional to. Now for example, if you look at your kinetic energy, it is equal to half m to the power v squared. So our mass is to the power 1. Now you might wonder to say, how did they find the values of 1 to the m to the power 1 and v to the power 2? So these cannot be known. So this is how we go with the approach. So the acceleration is proportional to, number 1, we have the velocity. Let's begin with our velocity to some power of m according to what we have been told, and the radius to some power of n, like that. So now we are required to know the value of m and n. So how are we going to do this? So we know that our acceleration is L t raised to the power negative 2. So we can be able to say L t raised to the power negative 2 should be proportional to, what is our v? Our velocity is a unit of velocity should be equal to L t raised to the power negative 1, or rather v should be equal to L over t, whichever is easier. So we can say that L to the power t raised to the power negative 1, then we have our m, like that. Then we are going to have our radius. Our radius is just distance. So since it is distance, it shall be assigned the dimension length, which is L. So we have L like that. Then it is raised to the power n. So now what we are going to do is, so we have our L t raised to the power negative 2 should be proportional to our L to the power, this m can be distributed. We have L to the power m, t to the power negative 1, like that. Then we also have this n comes there, so we have L to the power that. Then what we are going to do from here is, we have L t raised to the power negative 2 for acceleration. We want the values of m and l. so it should be proportional to, we have our L, then we have our M. L, it is to the power 1. As long as we are multiplying, we can add the power, so we have plus n. Then we have our t raised to the power -1, like that. So already so this m was distributed, so we are going to have L to the power m and our t to the power -m, like that. So even here it should be -1m, like that. So what we are going to get is we can say that this is L t raised to the power -2 should be equal to, immediately we introduce the equal to sign, we are going to say k, then we have our m, then we have our t raised to the power -m, like that. So from here, what we are going to do is we are going to equate. So let us equate our t with t there. So we are going to have our t raised to the power -2 should be equal to t raised to the power -m, like that. So already, if according to the rules of indices, if the bases are the same, you can equate the powers, so cancel that. So we have -2 should be equal to -m. We divide by -1, we divide by -1, then our m value should be equal to 2, like that. Then the other value that we are going to get is, we are going to get our L to the power 1, this is the same as L to the power 1, should be equal to L, the one with L, it is L to the power m plus n, like that. So after doing that, we can cancel this and this. So we have our 1 should be equal to m plus n, like that. Then what we are going to have is, we are just going to substitute. Where there is m, we put a 2. So we can have 1 should be equal to 2 plus n, like that. So we are going to have 1 minus 2 should be equal to n. So our n value should be equal to -1. So we have our m should be equal to 2. Our n should be equal to -1. And we have written our equation to be A should be equal to K. Then K, this one. Okay, so we have directly proportional to V. So we had is directly proportional to V to the power m, then our R to the power n, like that. So we just replace. So we have our A should be equal to, immediately we introduce equal to, we say K, V to the power m, then R to the power n. So our A should be equal to, we have our K, then we have the velocity, then m is power 2, our R is -1, like that. So we have our A should be equal to K V squared. This R -1 can be written as over R, like that. So this is our acceleration, like that. So this is our formula. So for this question, a planet moves around the sun in a circular orbit. The time period of revolution t for a planet depends on the radius. So they are telling us that the period depends on the radius, so we are going to say r, but we don't know the power. So this is depends, it is a relationship. And the mass of the sun, so we are going to say the mass to the power of b. Then we have the gravitational constant g to the power of c. So out of all these terms, the only thing that will be difficult for us to find is the dimensions of g. So we know that our gravitational constant, according to Newton's gravitational law, we know that the force should be equal to the gravity, or the gravitational force is equal to the gravitational constant times the mass number 1 and mass number 2 over the radius squared. So this is the formula we use to find the force exerted by two objects in space. So now we just want to find out what are the dimensions of this. What are the dimensions of g? So the dimensions of g are such that we have the force, the gravitational force. Let's just call it the gravitational force, like that. Then we have times our r squared. If we cross multiply like that, this f times r squared should be equal to g m1 m2, like that. Then we are going to divide over our m1 m2 like that, over our m1, m2 like that. So already this is our g. So our g should be equal to the force times the radius squared over the mass 1, then mass 2 like that. So already we know that our f, which we have constantly been deriving, it is equal to mlt raised to the power negative 2. So our g should be equal to mlt raised to the power negative 2. Then we have r squared like that over our m1, m2 like that. So now these are our dimensions. So regardless of the mass, it is still a mass. Whether it's mass number 1, mass number 2, it's still mass. So our g becomes equal to, we have our mass lt raised to the power negative 2 r squared. So we can just have one mass. So this could be mass times mass, since we have m and m there. So this is g should be equal to, we have our mass lt raised to the power negative 2 r squared. Then we have over our mass times mass is mass squared. If we want, we can just be able to cancel out. So this mass cancels with this mass, so that we have over the mass that is just down here like that. So what we are going to do after this is now our g value should be equal to, we have l t raised to the power negative 2 times the radius is equal to length to the power of 2 like that. Then we divide this over the mass like that, because the radius is a unit of length. So we have that. So we are going to have our g should be equal to, bringing the m up, we are going to have m to the power negative 1. Then we are going to have our l, then we have our l squared times this l, it will be 1 plus 2, which will be 3. Then we have our t raised to the power negative 2. So this is our gravitational constant dimensions. So we can now be able to answer. So we can now be able to replace the dimensions. So what we are going to have is our t like that. Then we put that. We can say should be equal to, immediately we say equal to k. Then the r is the unit of length. So we are going to say length to the power of a like that. Then we have the mass to the power of p. Then we are going to have the gravitational constant, which is our m negative 1, l to the power 3. Then we have our t to the power negative 2. So if you want, it's good, you can just memorize the gravitational constant dimensions. So that is what we have. Then we are going to now be able to simplify where possible. So this is the same as having our t on this side should be equal to k. Then we have our l to the power a. Then we have our m to the power of b. Then this power c can be distributed. So we have our m to the power negative c. Then this c times 3, it will be l to the power 3c. Then t negative 2 times c, it will be t raised to the power negative 2c like that. So if that's the case, we are going to have our k. Then we have l to the power a. Then this m and this m can add. So we are going to have times our m to the power, it is b. Then we are multiplying, but this is negative, so it will be minus c. Then we have our l to the power of 3c like that, times our t to the power negative 2c like that. So this is our t like that. So we can say t should be equal to, we have our k. Then this l times this l, it will be l, the power is a, so we add the power, so we have plus 3c. Then we have our m, then we have b minus c. Then you have t raised to the power negative 2c like that. So from here, what we are going to do is we are going to begin equating. So now, principle of homogeneity, whatever units are on the other side of the equal sign are the same as the ones that are on this other side. So already we should have m even here, but to maintain the meaning, we are going to say m to the power 0. M to the power 0 is 1. Then we also have our l like that to the power of 0, so that it remains, the meaning retains the same. So our t can be equated to this. So we are going to say our our t should be equal to t raised to the power negative 2c, so that already we cancel this and remain with the power. So we have 1 should be equal to negative 2c, like that. Dividing negative 2, negative 2, we are going to have our c value will be equal to negative 1 over 2, like that. So after finding our c value, we can also equate now the L. Let's begin with the L. So this L should be equal to the L that is here. So we have L to the power of 0 should be equal to L to the power a plus 3c, like that. Then we are going to cancel this. We are going to have 0 should be equal to a plus our 3c, like that. So we know that our c is equal to, we have found it to be negative 1 over 2. So what we are going to do is we are going to say 0 should be equal to a plus 3. Where there is c, we put negative 1 over 2, like that. So we have 0 should be equal to a, then negative half by 3, it will give us negative 3 over a 2, like that. So what we are going to find for a, taking the 3 over 2 this side, we are going to have a 3 over 2 should be equal to a. Finally, getting the m, we are going to have m to the power of 0 should be equal to, we have the m to the power of b minus c. This will give you, you cancel this, we are going to remain with 0 should be equal to b minus c, like that. Then our b should be equal to, taking the c this side, it will be c should be equal to b. And we know that c is equal to negative half, so we can just say negative half is equal to b. Now for the equation that was saying, that we came up with our t should be equal to k, then we have our r to the power of a, m to the power of b, and our g to the power of c. So we have found our values. Our c is equal to negative half, our a was found to be 3 over 2, we can replace. So we are going to have our t should be equal to k r, where there is a we put a 3 over 2, m, where there is b we put negative half, then where there is g, we are going to put g, where there is c we put negative half, like that. Now the question was asking that show dimensionally that t squared is equal to, or is directly proportional to, r to the cube. So how do you show this? So what we are going to do is, for this equation that we have, since we want t to the power 2, let's see what happens if we square both sides so that we can have that value. So let's square here. We also square the O of these. So we are going to have the square of this. So as long as I square both sides, it means to say I haven't changed any meaning. So it will be t squared should be equal to, this power 2 can be distributed. So we have k to the power 2. Then we have our r to the power of, we have our 3 over 2. Then this 2, it's the same as multiplying. Then we have our m to the power negative half. Then we multiply by 2. Then finally we have our g to the power negative half. Then we multiply by 2. So what we are going to get is a k squared. Then we have this part, this 2 and this 2 cancel. So we are going to have r to the power 3. Then we have our m to the power of, we cancel this, we have negative 1. Then we have g, like that. Then we are going to have g to the power of negative 1. So our t squared should be equal to that. So already, as you can see, we just want a relationship. So a relationship can just be an extraction. So already, as you can see, this is t to the power 2, then this is t to the power 3. So we can say that t is directly proportional to the r to the cube. So this is the relationship. If you want, you can say t squared should be directly proportional to g raised to the power negative 1. It doesn't change the meaning, but for this question, since they just want this relationship, you will have to get this. So, and not this. But it's a relationship. I just wanted to show you to say, even if you were to get this, if you were to get this relationship, this is a relationship of how if t is squared, what happens to chi? But they want you to show that t is directly proportional to r cubed, which we have ended up with those powers. So our problem, and our second problem, is saying obtain by method of dimensional analysis an expression for a surface tension of a liquid rising in a capillary tube. Assume that the surface tension depends on the mass, pressure, and radius of the tube, and constant is equal to this. So now we want the relationship. So already tension is a force. Tension is a force. So if tension is a force, surface tension is the force applied per unit length on a surface. So it is the force applied per unit length. So already it is more like surface tension is, let's say surface tension is the force per unit length. So this is where we are going to get our dimensions. So we already know and have established that our force is equal to our ml t raised to the power negative 2. So we know that our force is equal to ml t raised to the power negative 2. Therefore, the surface tension will be equal to we have our ml t raised to the power negative 2 over the length. Since it is the surface tension, let me just use t is force over the length. So this is what we have done. We can cancel this, we can cancel this. So the surface tension becomes equal to m t raised to the power negative 2. So this is our dimensions for the surface tension. So for this equation where it says obtain by method of dimensional analysis for the surface tension of the rising of a liquid rising in a capillary tube, assume that the surface tension depends. So we have the surface tension depends let's say surface tension depends on the mass, but we don't know the power, so we are going to say A. Pressure, power B. Then we also have the radius to the power of C. So if this is what we have, we can just replace the dimensions. So now pressure we discussed to say it is the force over the area, and our force is m l t raised to the power negative 2 over area, which is a unit of length to the power 2. So our pressure in this case is equal to our m l raised to the power negative 1. So our L minus 1 is negative 1. Then we have our t raised to the power negative 2. So we are going to have our surface tension is given as our m t raised to the power negative 2 should be equal to, then we have our m to the power of a. Pressure is given by the units of m l negative 1 t raised to the power negative 2. Then we have our radius. Then we are going to have our r, which is the unit of length to the power of c, like that. So after doing that, so here we are supposed to put the power of b. So after doing that, we can be able to say m t raised to the power negative 2 should be equal to m to the power a. Then we have our, this power b can be distributed. Let's just write it properly. So if it is distributed, we have our m to the power of b and our l to the power of negative b. Finally, this b times negative 1 is negative b. Finally, we have our t raised to the power negative 2 times b. It will be negative 2b, like that. So this is what we have. So therefore, we can first simplify things. We even have the l. Let's just delete this. So we even have the l, which is our l to the power c. So we have times our l to the power of c. Or we can just write l to the power of c, like that. So now already we have that. So let's simplify. So we have our m to the power mt to the power negative 2 should be equal to, so this m to the power b, let it multiply. So it will be take one m, add the power, so it will be a plus our b. Then finally our L to the power of negative c, add it, it's L to the power negative b, this one, so you are multiplying L to the power negative b times L to the power c, it will be plus c like that. Then we have t to the power negative of 2b like that. Finally we are going to have our m, we are going to equate, so this m and this m, so we are going to have our m to the power of 1 should be equal to m to the power of a plus b like that. The other equation that we can equate, so here if you can see the L, it's there, but the power is 0. So let's get even our L. So L to the power of 0 should be equal to L to the power of negative b plus c like that. Finally, we have our t raised to the power negative 2 should be equal to the t raised to the power negative 2b like that. So already that means to say we are going to equate them. Let's begin with this one, since this one is the one having just one variable. So we can say our t raised to the power negative 2 should be equal to t raised to the power negative 2b. So we are going to have this one and this one will cancel. So we have negative 2 should be equal to negative 2b like that. Then we are going to divide negative 2, negative 2. So our b should be equal to positive 1. So getting this, we can cancel m. So we are going to have 1 should be equal to a plus our b. So we are going to get 1 should be equal to, we have our a plus our b is equal to 1. So our a will be equal to 1 minus 1 if the 1 goes the other side, which should be equal to a. So our 1 minus 1 should be equal to 0. So 0 should be equal to a. Doing the other one for L should be equal to L to the power negative b plus c. So we are going to cancel this and equate the power. So we have 0 should be equal to negative b plus c like that. So what we are going to get is we want the value of our c. So our c is equal to, we take the b this side, it will be positive b should be equal to c. And we know that b is equal to 1. So we are going to put 1 should be equal to c like that. So we have found our a to be equal to 0, b to be equal to 1, our c to be equal to 1. So we said that the surface tension, our T, should be directly proportional to, according to this, we have should be directly proportional to, the equation that we wrote was directly proportional to our mass to the power of A. We also had our pressure to the power of B and our radius to the power of C, like that. So what we are going to have is substitute. So first we have the surface tension. Surface tension should be equal to K, constant. Then we have the mass to the power A is equal to 0, pressure to the power 1, radius to the power C. So what we have is, we have a K PR, but we know that K is equal to half, so we can be able to put our half, then we have PR. We can even go further. We know to say the pressure of a liquid is given by the formula of the density of a liquid times the gravity times the height. So we can just, where there is pressure, we can just put this and say that our surface tension should be equal to, we are going to have our half, then we have pressure, gravity times height. So this is our final answer for that problem. So we have this other question: the wavelength of associated with a moving particle is dependent on its mass m, velocity of motion v, and the Planck's constant h. So show dimensionally that the Planck's constant is equal to that. So we are going to say that since they are saying that the wavelength, so we have the wavelength is directly proportional to our wavelength is directly proportional to the firstly the mass, so we are going to say mass to the power of a. Then we have our velocity to the power of b. Then we have the Planck's constant h to the power of c. So what we are going to have after this is we are going to replace. So the only challenge would be the Planck's constant. So the dimensions of the Planck's constant, you can just think of the energy times second, or the energy times time. This is what you can think. This is not the formula, but this is what can help you. Energy, just get any equation of energy. Let's say the potential energy is equal to mass times gravity times height. So we know that the gravity is also called acceleration, and acceleration takes L t raised to the power -2 like that. So our h should be equal to, we are going to have our energy, which is our m, forgot, so gravity is m. So here we can replace, where there is g, we are going to say potential energy should be equal to mass, then gravity is L t raised to the power -2. Then we have our h, which is height. So the height is equal to the length L. Height is also length. So we can say that the potential energy, which is just energy, is equal to ml squared t raised to the power -2 like that. So we can replace, for where there is h, we can say the energy second, which will be our ml squared t raised to the power -2. Then we have times the time, which is capital delta T, should be equal to, we have ml to the power 2. Then we are going to take 1, then add 1 like that. So our h should be equal to our ml raised to the power 2. Then we have our t raised to the power -1 like that. So these are our dimensions for the Pascal, for the Planck's constant. So let's get our equation. So we are going to replace our wavelength, which is our wavelength is just a unit of length, should be proportional to, we have the mass to the power of a, then we have the velocity to the power of b, then we have the Planck's constant, which is our ml squared t raised to the power -1. Then we have our c like that. So after doing that, we can simplify things. So we have L is proportional to have the mass to the power of a, the velocity to the power of b. Then we have this c can be distributed, so it will be m to the power c, L to the power of 2c, 2 times c, it will be 2c. Then our t raised to the power -c like that. So after doing that, we can say that this is our power 1 like that. So let's simplify things. So we have L to the power 1 should be directly proportional to m to the power of a times, so we take 1m and add the power, so it will be m to the power a plus c. Then we have times our velocity. So our velocity will take the units of, we know that velocity is L t raised to the power -1 like that. Then we are going to have our mass to the power of c. Then we have already used the mass to add here, so we are not going to put it there. So we have our L to the power of 2c like that. Then we have our t to the power -c like that. So we are going to get our L to the power 1 should be proportional to the mass to the power of a plus c. Then we have our L can add up, so we have L to the power 1. This is the same as to the power 1. Then L to the power 2c can add, so we have plus 2c. Then we have our t to the power -1 can add up to give us -c like that. So our velocity was to the power b here, so it is supposed to show. So distributing the b, we are going to have our L to the power b, t to the power negative b like that. Then we have our L to the power of 2c. Then we have our t raised to the power negative c like that. So this is L to the power 1 proportional to mass to the power of A plus c. Then we have here now. So L is common, so we get one L and add the power. So we have b plus our 2c. Then we are going to have our t to the power of negative p. Then we are going to subtract, since yes they are multiplying, but since one is negative, so t times this t, we take one t and subtract the powers. So this is what we have. So we are going to have our L to the power 1 is proportional to m to the power of a plus c. Then we also have L to the power of b plus 2c. Then we have our t to the power of negative b minus c like that. So this is what we have. So we are just going to equate. So even here the mass is there, but it's power 0. Even our t is there, it's also power of 0. So we can equate to say our m to the power of 0 should be equal to our m to the power of a plus c. Then we also equate our t to the power of 0 should be equal to t to the power of negative b minus c. We also know that our L to the power of 1 should be equal to our L to the power of b plus our 2c like that. So we have our 2c like that. So already that means that we are going to have three equations. So we have this one cancels with that. So we are going to have 0 should be equal to a plus our c as our first equation. Getting also this one and this one goes, we are going to have our negative b minus c. So we had the 0 here. So 0 should be equal to negative b minus c. Then we also had this one and this one cancel. So we are going to have 1 should be equal to b plus our 2c like that. So we have three equations. So the ones that are similar the most, it's these two equations, since they both have b and c. So we can solve them simultaneously by saying 0 should be equal to negative b minus our c like that. Then we have 1 should be equal to b plus our 2c like that. So already we just add them. So adding, this is 0 plus 1, it will give us 1. Then we are going to have negative b plus b. It will be 0 because negative b plus b, this one is positive, that one is negative. So those end up cancelling. It's okay if you don't write the 0 there. Then you have negative c plus 2. So negative c plus 2c, it will give us a positive c. So this means that c is equal to 2, or c is equal to 1, sorry. If our c is equal to 1, we just get any of the two equations. Let's say we get 0 should be equal to negative b minus c. So what we are going to have is 0 should be equal to negative b. Where there is c, we put 1. So taking the 1 the other side, or just taking the b the other side, since we want to make b the subject of the formula. So we are going to have b should be equal to negative 1 like that. So we have our negative 1 like that for our b. So knowing that our a is equal to negative 1, our b is equal to negative 1. So we know that we wrote our expression to say our wavelength is directly proportional to our mass to the power of a. Then we also have the velocity to the power of b. Then we have the Planck's constant to the power of c. And we know that our wavelength will now be directly proportional to our mass. The a is equal to the power negative 1. Then we have our velocity to the power of b, which is negative 1. Then the Planck's constant to the power of 1 like that. So the wavelength is directly proportional to, we are going to write the h over, because this is negative 1, it can be written as m down. Even this velocity can go down if we remove the negative. So we have shown, so we can say hence shown. Thank you very much for watching. Hope you would like, subscribe, and share for more.